Hello everyone, this is Analog Circuit Design Differential Amplifier Part 2. I'm Tae Kang. I would like to acknowledge my advisor Michael Flynn and then also Dr. Seung-Jong Lee. Here's our outline. First, let's see the active loads and CMFB. In the previous lecture, what we learned was resistive load differential amplifier. But when you think about the CS amplifier, we learned that the RD, the resistor as a load is not good because the large signal resistance and the small signal resistance are the same. So that's not good because here VDD Vout DC was RD minus, VDD minus. It was VDD minus RID, RD, right? And also the gain was minus GM RD. So since, and then this is DC voltage, DC. So because RD is in both DC output voltage and then the gain, so it's kind of, we don't have enough freedom to choose, right? Because what we want is we want to increase the gain, which means we have to increase RD, but we cannot increase RD because of the DC voltage of Vout. So they are tightly related, so it's not good. So here's the same. We want to, here RD, we also have to care about this Vout DC voltage, right? We have to care about this Vout DC voltage. In that case, here is the same. Vout DC is VDD minus, well, in this case, ISS over 2 RD, and then gain was also GMRD. So there, we don't have any freedom. So what we can do is we can use active loads. So here we use a resistor. Not resistor. We can use a PMOS. In this case, the gain would be GM and then RO1 parallel RO3, right? So this would be the gain. So and then what we can also do is a cascode. We can use cascode to increase the gain, right? And then that's here, which is cascode this part, and this part. So in this case, the gain would be, we can amplify. So cascode amplify the resistor, right? So the gain is larger than that. And then the reason why they use both cascode is, if you just use one cascode, then the parallel resistor is like limited by the smaller portion, right? A smaller weight part. So if you just use one cascode, it's not that effective. So that's why we use both cascode. So we can get active load, we can get a higher gain by using cascode. But what's the bad part? Headroom. Headroom is a problem because you see that how many MOSFET should we stack? 5 of them. So it's like 5 MOS stack. It consumes a lot of headroom. And there's the diode connected load. This is same as the common source amplifier that we learned. So for this one, the gain would be minus GM, GM1, so this one. And then the impedance to look into there is that's GM3, 1 over GM3, right? And here we can increase the gain a little bit by putting this extra branch. So here, this part. So in this case, the current flows here would be 0.2 is over 2. So to set this, we can properly set this value. For example, we can use current mirror to set this. In this case, the gain would be here. Well, there should be minus sign, and this is the reason. The way how we can get is GM is this one. So we have this. There's a GM form of this. So by using it, the GM1 would be UN COX W over L1 and then ID1, right? And then because the resistor looking here, this is, let's say, just infinite, because the resistor here is small. So what I'm saying is this way, this is 1 over GM4, but this way, this is RO4, or RO6. And 1 over GM4 is a lot smaller than RO6. So that's why we can just ignore this. The output resistance, we can ignore this. So this would be mu p. Here's mu p, right? Because M3 is PMOS. Mu p, same COX, W over L, in this case 3, ID 3. So that's what it is, because COX is the common. So in this particular example, this would be ID1 is 1 over 2, well, ISS over 2, right? But the current is 0.2 ISS. So here, 0.2 ISS. So it turns out UN mu P, well, this would be P. And it's like square root 5, right? Because 0.2. So we can have like little larger gain than this by using it. Here we need to discuss about common mode. This is very important part. And then this is like a difficult part, a tricky part of the amplifier design. So this is tricky, but important. So we want to define the common mode of Vout well. So the Vout is actually really sensitive in this case, because the like this is just a MOSFET, maybe PVT variation, or the input level can be changed. So these are not that well defined with only this circuit. So also, for example, if Vout is too high, if Vout is, let's say, Vout too high, then M3, M4 will be in linear, or if Vout is too low, then M1, M2 in linear. So we also learned that in the previous slide, there is a certain Vout level. And then there's the other reason that we want to set the common mode, because this Vout goes to the next circuit. Could be next circuit, could be the other amplifier, or the other circuit, as a point of view from the next circuit. So next circuit also wants well-defined Vout. So we need to do something about Vout DC level. What I'm saying is Vout DC level. And there's like a requirement. The ID1 and ID3 should be the same, and ID2 and ID4 should be the same. So what it means is these currents should be same, so they're balanced. If, let's say, if ID3 is larger than ID1, then Vout will just go up. Well, actually, also setting this current the same, so because it means that we have to set VB properly. So it turns out this means that set VB properly, and that's hard actually. So this is hard part, because even if you use like a current mirror, their current, it's kind of hard to set it same. So we need to set the VB properly so that M3, the current to ID3 should be ISS 2, and that's kind of difficult. If this VB is like wrong, then VL will change, right? So it will eventually, this VL will go to some stable point, but that point will not be like in a good position. So again, so here the question is how do we set this value? So VDS3 and VDS4 means like VL DC. So how can we set VL DC well? Like, which means that how can we set VB properly? So for fully differential mode, we need common mode feedback, which is CMFB. It's very widely used. It's like a fully differential amplifier needs CMFB. And what is fully differential? Fully differential means input differential, output also differential, right? You see that input is differential and output is differential. This is fully differential. So for a fully differential amplifier, we need this common mode feedback. Let me just show you like a brief like system diagram. So this would be common mode detect, and then this will go to some amplifier, and here would be VCM desired, and this voltage will go here. Let me just draw again. Here. So what happened is, let's say this VDD is 1 volt. Let's say this is 1 volt. (1.0 volt), and then VCM desired is 0.5 volt. It's like, which is half VDD, right? And then assuming the Vout is at first like 0.6. What happened is VCM detected, so this is also 0.6, right? But our desired value is 0.5. So 0.6, 0.5. This value would go up, right? Does it make sense? Because now Vout is 0.6 voltage and the VCM is 0.5 volt. So the output of this amplifier is like high value. And that would change the V bias. So here V bias. What happens is if V bias goes up, so if V bias goes up, this PMOS gets weak, right? So does PMOS try to flow current low? But we do have this ISS current source, right? So VL should go up. right? Because again, what I'm saying is this will change. So this increasing change VGS3 down, right? Does it make sense? If we increase, if the voltage here at the output of the amplifier increases, VGS3 change decreases, right? Because this is PMOS, VGS is here. So here's plus minus VGS3. So VGS3 is decreasing, but we need to keep ISS over 2. So it turns out VDS3 increases, which is Vout decrease. So this will go to 0.5 eventually. So it's like a loop. There's another feedback loop, and then that controls the Vout voltage. So this is tricky because there's another loop, and then we have to consider lots of things, but it's very necessary. And then this CM detect, this can be like, this can be the most simplest way to do it is here. Is Vout 1, Vout 2, and then this value is this. So like the resistance can be really large because it shouldn't impact the operation of this amplifier. So this can go here. That's one way to implement it. So again, the way our purpose is, we want to set this V out at certain voltage, like 0.5 volt, for example. Then we need to control this VB. So CMFB in this case, I mean, there's a lots of CMFB. We can also control maybe some other voltage, maybe here, or there's the other. If we have other stage, then we can control there. So anyway, in this example, the CMFB is control VB. Okay, that's the goal. Well, let me just say it like properly set VB. That's what this common mode feedback does. And since we have this feedback loop, if this V out is too high, then this amplifier will control this VB. This one, VCM desired, this is provided from the outside. Maybe we can just use simple like VDD. This one, right? This can be also VCM desired, right? Let's say here's some, there's R and R, same R, then VCM desired will be VDD over 2. So that's common mode feedback. We try to control this Vout DC voltage. Set Vout DC. Next, let's see the frequency response of these active loads. Frequency response of this differential pair is actually easy. It's just identical that we learned because this P, node P is AC ground, right? We learned about this at the previous lecture. So this will be AC ground. So we can cut half this differential circuit, and then it will be RD and M1 still, and this is AC ground. And let's just assume that there is RS, input resistance, because that's what we learned. There's input resistance. I mean, this is parasitic resistance, right? We do have parasitic. It doesn't mean that we are putting resistor intentionally. This is like parasitic and Vin. And so we have this have this CGD, and let's say CL, C load. So this includes CDB or yeah, CDB, and then to CL, the next next circuit, and here is a CGS. So you can refer lecture 14, which is frequency response. So the answer is the same. We do have a pole at node. Here's X, and then let's say this is out. Then so pole X is, so we have to consider Miller effect. And then the answer is, so you can get this answer from lecture 14. CGS plus 1 plus GM RD and CGD. So this is Miller effect, right? Miller effect. And we also have the other pole at the output. Or let's say just write it here. W out would be simply 1 RD CL. We also have 0, right? C was GM. Well, if we assuming that this parasitic RS is too small, then we can ignore this. Because RS is 0, then this goes to infinite. And this, the next sentence means that, by the way, overall there is just one pole at the output, not two. It means that when we see this circuit, we have two nodes, right, at the output. But we only consider just this one single node. Why? Because they are symmetric. So we have to consider only a half path because their operation is exactly same with just a different phase, I mean opposite phase. So each of them has a pole, but they're like the same thing because we can just consider this two circuit as a like two pieces. So again, even though there is two nodes, since this half and this half operates exactly the same, we can consider that we only have one output pole at this node. Oh, well, I'm not saying at this single node, we do have output pole at each node, but they are the same. They are same frequency, and then they work as the same. So when we think about the frequency response, we only have to care about this half, and then we can say we have one single pole at the output. I mean one pole at the output, not two nodes, just one pole here. And here's the frequency response of active load. Dump all parasitic capacitance to ground into CL. It means that CDB1, like this capacitor, CDB3, this capacitor, and CDG3, this capacitor. So those are AC ground, right? So here is actually AC ground. So that's why we can just merge these three capacitance to the CL. Again, to clarify what CL is the load capacitance. Because when we use amplifier, it means that we need to drive something, right? Amplifier, let's say, so this is the amplifier, like V in, V out symbol. When we use amplifier, it means that we need to drive something. Let's say there can be another amplifier, right? So this is C load. because if the another amplifier attached follows our target amplifier, it has its input capacitance, right? So that's C load. C load means whatever the circuit comes after our amplifier, that's C load. So normal capacitance is to ground here, and then we can just use a small signal model like this, and RO1 is here, and RO3 is this PMOS, and then we can just calculate. If we have like input resistance RS, then we can also consider this RS and then solve the small signal model. Next, let's talk about active current mirror load. So why do we need active current mirror load? We can just see this two kind of problems and then that's why we need sometimes we need active current mirror load. So for example, sometimes we need single-ended amplifier because we just learned that fully differential amplifier, but sometimes we want the input to be differential but output to be single-ended. For example, what if we need like a unity gain buffer? So the way how it works, let's say we have 0.5 volt, and then let's say this is 0.6 volt for just a random initial value. Then since here is 0.6, the output will go down, right? So it goes to 0.5 volt eventually, and so it also goes to 0.5. That's how like we get a exact same voltage. To implement this unity gain buffer, we need differential input and then single-ended output. So that's why sometimes we need single-ended. And also, how about common mode of the output? So in this fully differential amplifier, we need CMFB, but for active current mirror load, we don't need we don't need common mode feedback. So that's good, right? So if we use active current mirror load, we can achieve single-ended amplifier, and then also we don't need CMFB. Here's the schematic of active current mirror load. So this connection is the key. So what we learned before was the fully differential amplifier they look like this. Right? Or they just look like resistor there and this. So if we compare this with this, we need some V bias externally from this fully differential amplifier. But in this active current mirror load, we don't need the outside bias voltage. So this sets up biasing, and also it sends left output to right side. So it means that if the input is differential, right? If this input increases and this input decreases, that's differential, right? If one is increasing, one increases, then the other decreases. So if this increases, what happens is the current will increase, right? Because GM increases. So ID increases, and since there's a mirror, here also MID4 increases. How about here? How about this node? If this decreases, then the current decreases, right? So in this case, ID2 decreases. So the direction would be ID2 decreasing, then this one is upper side, right? And then if ID4 increases, then it's pouring the current here. So it turns out they are summed, and then the net current will flow here at the outside, right? Does it make sense? So again, if the voltage here changes, this change will flows here and then impact the current flow here, and then this decreasing voltage will also change the current here. So this M1 changes the current here, M4, and then this node changes the M2 current. So that's how sends a left output, so which means here sends a left output here to right side, and this is called as operational transconductance amplifier, OTA. And also you can refer to Razavi 5.3 section active current mirror. So this is active mirror because the signal is mirrored here, unlike just this DC bias. In this DC bias, for this fully differential amplifier, this DC bias is just constant, right? Unlike there, in here, this bias voltage is also active, right? This bias voltage reacts to the input, and it goes to the output. So it's there like two paths. So it's active current mirror. Next, let's calculate the gain. First, simplified version. So how does bias works? First, assume V in diff is 0, which means VG1, VGS1, and VGS1 is VGS2. So in this case, tail bias, which is ISS, splits between M1 and M2, right? So in this case, ID3 is ISS over 2, and then ID4 is, because if here the ISS over 2 flows, then it can set the bias value here, right? So it's kind of it's a current mirror, and then M4 there will be also ISS over 2 flows. So ID4 would be also ISS over 2. So now have ID4 is ID3, which is ID2. So, well, everything is balanced. Let's calculate the small signal gain with this circuit. So we'll do some assumption, which is the circuit appears symmetric from M1 and M2. So it means like here, it's like in the lower part of the circuit they are symmetric. Then what happened is the node P is getting a virtual ground. So for now, let me just write it down in the other color. For now, assume node P is like a small signal ground. So we will just assume that P is ground, because we can just that these are symmetric. So it's like actually if there's a P node and then it's like a pivot point and then they're like balanced. So that's where we start, assuming that this is AC ground, right? AC ground. If you assume the circuit, the node P as AC ground, we can redraw the circuit like this, right here, and assuming that we apply input, which is plus V in over 2 and then minus V in over 2. Again, this is small signal gain, which means the actual V in will be like this. There will be VCM, and then here there's VCM, and this will be V in over 2, and then this will be minus V in over 2. That's how it applied to here, to the input. And then since this is small signal, we will only consider about these delta, like delta, this one, okay? And then let's say here's node X. The Vx would be, Vx change would be, let's say the delta Vx is, we have a, this is GM1, right? So GM1 minus GM1, and what's the impedance at this node? That's like GM3 over 1, right? And then our delta V in is V in 2. Again, this is small signal V in. So this is, well, just write it down as V. And then this is small signal V in. And since Vx changes, right here, Vx changes, we're going to say delta IM4 is GM4 times delta Vx, right? So it would be minus GM1 and GM4, GM3, V in over 2. But we'll assume that M3 and M4 are the same, or same size. So we can just say M4, GM4, and GM3 are the same. So this will be minus GM1 V in over 2. We need to note that this is delta IM4, where IM4 is here, this IM4. So it's current change. So what we calculate was from here into this. We haven't discussed about this part yet. Now let's think about the other half, from here to the output. So in previous slide we got a delta I here, right? Delta IM4 was GM1 V in over 2, right? We also want to check the current difference from here. So that will be delta IM2, where we define the direction of delta IM2 is to the ground direction, and that will be GM2 times delta VG, right? Times delta VGS2, which is minus GM2 times V in minus V in over 2. So we got this 2 change, and let's assume GM1 is GM2. and the direction is kind of tricky. So delta I M4 goes to down, and delta I M2 goes to down. But the polarity of delta I M2 is what? Minus, right? So this is because minus GM2 2 over V in. So in net, delta VM2 out is going to this way, and then delta IM4 is going to that way. So we can add them. So the current to V out, the current to V out is delta IM4 minus delta IM2, which is GM1 V in. And then we will calculate V out. So V out would be current times resistance, and that's GM1 V in times RO2 RO4. So the gain is GM1 RO2 RO4. So this is the final answer. Well, so now let's look at more like a little more accurate way to calculate the small signal gain, because in previous slide, what we assume is this is symmetric, right? That was our assumption. That was here assumption. So now we're using a more accurate way. We're going to use Norton equivalent. AV is minus GM R out. To just little reminder, this is effective transconductance. Transconductance with Vout connected to AC ground, which means small signal ground. That's GM, large GM, and our out is resistance at V out with input at small signal ground. So it says the voltage source will go to short, and then the current source will go to open. First, let's find the GM. Well, actually, this is similar to previous method where we assume symmetric, but we will explain how can we use this metric. So to find the GM, what we do is we need to short. This is AC short, AC GND ground, the output, and then we will see the I out over our voltage change, right? So in this case, the impedance here is 1 over GM3, right? And the impedance here is 0. So if we write it down, it's a first resistance at V out is 0, right? Because of this AC ground. Again, we're looking at in small signal. So the resistance at V out is 0 because we connected to AC ground. And then what about the resistance at node X? So that's 1 over GM3. Here what we can interpret is 1 over GM3 is what? It's very small. So we can assume that they are kind of similar. So these two similar. And that's how we can say, oh, so we can use symmetric. We can use symmetry. So now we can redraw this schematic like this, because since we can use symmetry, that means node P is AC ground, right? And the rest of it is the same as a previous method. So the GM would be GM1 or 2. So the end result, the conclusion is that we can use symmetry. So it's in this slide we show that by using this resistance and then this finding large GM, we can say at this stage the resistance through this way and then this way are both of them are kind of very small, so we can approximate the circuit to symmetric, and then we use like a from here and here. That's what we calculated, right? And then we got this GM1 and 2. So we got a GM, the effective transconductance. To find R out, what we have to do is first input ground, right? Input ground and current source open. So input means a voltage source, right? Input is voltage. So here the input is ground and then current source. There was a current source, right? And then we just open it. And we have to apply Vx and Ix here at the output node. And this is V out. And R out is Vx over Ix. So it's from Norton equivalent. Let's look at this Rxy part first. So we can substitute it with something. M2, and then here's MOS. So there's 2 ports, right? And this looks like this 2 port. And we want to make it simpler. So if we calculate the resistance here, to see here, that's Rxy. And actually Rxy is RO1 plus RO2, right? Because at this point of view, there's RO1, and then in this point of view, RO2. So that's why it's RO1 plus RO2. and then this will be 2 R01. We'll just assume that R01 and R2 are the same. So with that, we can change the circuit like this, and there's R04, so this part is replaced by this 2 R01, which is RXY, right? And to see here, that's 1 over GM3 parallel R03, right? This part. So this 1 over GM3 and R03. And to look at here, R04, and we still put this, we still leave this NMOS because, you know, the voltage here changes. So this NMOS will work as a small signal model. So the equation that we can get here is that IX is, there are total 3 parts. First here, and second here, and then third here. So let's see the first one, first current. That will be Vx over 1 over GM3 R03 plus 2 R01, right? 1, 2. Plus, so that's number 1. So let's say this is number 1, this is 2, and this is 3. And what about 3? What about 2? So the current flows here, right? And that changes the voltage here. And that will also control this MOS, this PMOS, and then that will make the current flow. So let's see, if current flows here, what happens is the voltage here increases, right? Because V equal Ri. So if current flows here, the voltage increases. And the voltage increase of the ratio of that, so here's VGS4. Let's say this is VGS4. So VGS4 is the current, Vx1 over GM3 R03 plus 2 R01 2 times, we're going to use resistive dividing. So that will be 2 R01 2 plus 1 GM3 R03, and here will be 1 GM3 R03, right? That's GS4. And not this. Well, actually, we don't need resistive dividing. Actually, this is the current flows to here, right? So all we need is just this current multiplied by this resistance. So this will be 1 over GM3 R03, and then this is the voltage difference here, and then we're going to multiply by GM4, right? Because if this voltage changes about this much value, the PMOS will increase more current. They draw more current here, so we're going to multiply the GM4. So this will actually looks like they have a common term here, so we'll add it here. So that will be, I'll just say 1 plus this one, right? So 1 over GM3 parallel R03 times GM4. So this corresponds to number 1 current, and then this corresponds to number 2 current. And then we need number 3 current, right? And that's very simple, which is R04 Vx. We actually can make this thing more simple, we'll do a lot of approximation here. So what can we do is here first. This is, so R03 is a lot larger than 1 over GM3, right? So this will become 1 over GM3, which is a lot smaller than this one, right? So this will just go to 2RO1 2 Vx, and here 2. 1 same, and then this will be GM3 and GM4. And we can still have this term, which is Vx RO4. But here we say GM4 and GM3 are similar, so we can just say this is 1. So it turns out Vx RO1 2 plus RO4 Vx. So the conclusion is R out is RO2, or let's say RO1, while RO2 parallel RO4. Let me just rewrite it again. So the conclusion is R out is IX Vx, which is RO2 parallel RO4. So the overall gain is minus GM times RO1, RO2, RO4. Oh well, we write it down it's this way. So the gain is GM1, RO2, RO4. So the final answer is the same, right? Final answer between simpler one, assuming the symmetry. That's also we got this gain, and then also in here more accurate one. And when we calculate the R out, we didn't use the symmetric, so we do a full calculation, but because of that, this part like 1 over GM is smaller than RO3, so these things can go be negligible, substituted, and then eventually we got the same result. So it means that the symmetric assumption is kind of okay. So this is our final answer. And the other thing, that the reason why we call this circuit OTA, operating transconductance amplifier, is that it controls the current. You know, the output of this the circuit is current, so that's why we call this as OTA. Next, let's look at the common mode gain. Before the gain, let's talk about common mode range. So we'll think about VCM. So here we just assume that they are connected together, right? They are same VCM, and we will set the minimum value of VCM and then maximum value of VCM. So VCM is common mode input, right? We'll just remind you again. So VCM is here, and then the input will be here. This is V in 1, and then the other part will be like this. This is V in 2. So the common mode is VCM, right? The minimum common mode would be we need to place this M5 in saturation, right? So VP first. VP should be larger than, let's just say larger than VB minus VTH 5, right? And then this is, we can just say VDS set 5. Well, VD set 5. Set 5. Then VCM should be larger than VGS1 or 2 plus VD set 5, right? So VGS1, 2 is from here to here. So that's the minimum boundary of VCM. And how about V maximum? So the maximum now, what we worry about is M1 and M2. Why? To place this M1 in saturation, the drain voltage should be high enough compared to VCM, right? So if we set VCM too high, the VF is not, it cannot be too high either, too high. So to place this M1 in saturation, we need to limit the VCM maximum. So it's simple. VCM shouldn't be larger than this, right? Because the saturation condition would be VGS1 should be VGS1 minus VTH1 should be smaller than VDS, which is VG minus VTH1 should be, let me just larger, VD. So yeah, this would be plus. So VG is VCM and then VD is VF. So that's the range of operation. And then common mode gain. So here, since we assume that this VCM are connected, what we can do is we just represent it like this: V in CM, right? Well, this is a small signal gain, so we will say V in CM there, and then V, let's say bias. So this is small signal portion of common mode, So basically, due to a finite R out of M5 here, because that's not like a perfect current source, the bias current changes as VCM changes because of the channel length modulation, right? So if we change this circuit to a small signal model, so it'll be like this, and here we have RSS. That's when we consider about the channel length modulation. And here V in CM. Well, RSS is what? That's R05, right? So common mode gain is defined as V out over V in CM. So it's basically how much voltage of V out changes when we change V in CM. And is this, so what's better? What's good? Do we want to have larger ACM, common mode gain, or do we want smaller ACM? So we want smaller. We want small ACM, right? Because we don't want our common mode changes. I mean our output changes because of this our common mode, because that's not the input. Because because our interest is V in differential mode. Okay, we want the circuit only reacts to V in differential, not V in CM. So we model the tail source as a resistor here, right, which is RSS. And the analysis will be a lot easier if we have symmetry. That means if Vf is V out, then that's a lot easier. Is Vf and V out are the same? We can actually prove it like just a simple assumption. So assuming that like proof, so it's symmetry, then Vf is V out. So proof, assume, so we're going to use a contradiction. Use contradiction. So assume Vf is larger than V out. So due to the channel length modulation, then ID1 is larger than ID2, right? Because because of the larger VDS. Due to channel length modulation. But ID1 is ID3, right? And ID2 is ID4. So it means that ID3 is larger than ID4. So does it make sense when we see this PMOS? Which VDS is larger? So, because their VGS are the same. So VDS. Now here plus minus VGS3 is equal to VGS4. So is this true? No, that's not true because we assume that VF is larger than V out. So V out is smaller. That means, so it means ID4 is larger than ID3, right? Because of this. This is also due to, well, lambda, channel length modulation, right? So this is lambda. So you see that this and this are contradictory. So this assumption is wrong. So it turns out Vf is V out. I mean, the opposite way, we can also prove the same thing. So we got this. Vf is always same as V out. So thanks to symmetry, we can connect this F and X, right? Those voltages are the same. In the previous slide, we talked about that. So we connect it, and then we can change this to here. So we can change this to here. So we have RSS, and then since they are like equally connected, right? So it's like a finger or M. So the V in CM goes to here, but now we got double GM2. Again, these two are connected. All of their nodes are like their gates are connected, and then their drains are connected, their sources are connected. So we can just model it as a single MOSFET with doubled GM. And then since they're parallel, the RO1, 2 will be divided by 2. And here's the same. to see the impedance here, that will be the parallel between the half of 1 over GM and then half of our RO34. So if we calculate the gain here, so this is actually a degenerated CS amplifier with load RD, but we should remember that here RO1 is neglected. So here too, we're just going to ignore this RO1 too for simplicity, and this is also a huge value. So that will be like this, and this value is smaller than here, so we can also ignore this part, and then what we got is this. So this is a gain of common mode. And let's look at the common mode rejection ratio. So this is the definition. The common mode rejection ratio for the fully differential output circuit would be this. And for a single-ended output, which is what we're working on, is TM and then ACM. So here's our final result. This would be differential mode gain, and this would be 1 over common mode gain. Again, CMRR high, good, which means that we have more differential gain than common mode gain, because for a differential amplifier, what we want is we only want to focus on the differential input, not the common mode input. So we want differential gain larger and common mode gain smaller. Next is a frequency response. The key point of frequency response in this active low single-ended amplifier is that it has 2 poles. So do you remember in a fully differential amplifier, so here fully differential, we only care, so these 2 poles are identical because the signal flow, like from here to here or here to here, they're all symmetric, so it's very symmetric. That's why only a single pole existed in output. But unlike differential pair, the frequency response of this single-ended is not symmetric, so we will have different pole. So from this way, the output pole and then the mirror pole, they are different, right? So we have to consider about these 2 poles. So let's say here is capacitor E. So there are two paths to be out, as we said. So half of signal goes through M2, right? And also half goes through M3 and M4, well, which is M1 and get mirrored. To M3 and M4. So 2 paths, and they're different, right? So the path through mirror, so through here, they're like more delay, right? And get pole and 0 pair, right? Because it goes to gate and drain, and then we learn in CS amplifier frequency response that these paths will make 0. So let's do some calculation. Well, the final answer will be this. let's see how we can get. And here also CE. So this CE is like all capacitance summation of here, like it includes CGS 4, CGS 3, and like CDB or CDB1, and also like CGD1 and CGD4. So I just assume that there's lots of capacitance here, but just say CE at this node. What we can do here is this can be like 1 over GM3 AC ground, and also RO, not RO, but just ignore that, CE. And let's say here's M1. So what we said, and then here P will be just we see it's a AC ground. We're going to calculate V out. Okay. To do so, what we do is the V out would be the GM, the large GM times R out. This is what we're going to use. Okay. Well, just let's say minus GM. So that will be V out is the first one is just here, right? Just this path. So that would be GM2. And then the input would be V in over 2, right? Because it's differential input. And then this part will be a little tricky, and that's why I draw this one. So the other part will from this M1. So if this M1 voltage changes about V in over 2, then current increases, right? And then the current increases, and that will mirror to this M4, and then that will make current. Okay, so what we're doing here is the current from here and current from here. So this would be 1, and then we're going to calculate 2. So that's first from here, and this part is E. Let's calculate the voltage difference, voltage change in node E. That will be GM1 and 2 over V in. So that's the current change, and then we need to calculate the impedance here, and that will be 1 over GM3 parallel SCE1, right? So we got these two times R out. R out would be RO4 parallel RO2 times also parallel 1 over SCL. So this is V out. And then if you do some like just math, just fully calculated, and then we got this. So now what we see here is that we see 1 0 here, right? Because it has S, and then pole 1 and pole 2. Well, let's say this one has pole 1 and this one has pole 2, because this is dominant pole. So dominant pole means smaller frequency. So the dominant pole was W out, right, at the output node, which is minus 1 CL and RO. By the way, this RO is RO3 parallel RO4. Okay, that's also same for the previous slide. So that's our dominant pole, and then high frequency pole, which is from here. This is high frequency pole, and that will be WPE, right? And that's GM3 and CE. And 0. 0 is WZ, and then that's, and also that happens at node E, and that's GM3 and so 2 GM3 and CE, because you see at this part, right? So if we draw a graph, the dominant pole comes first, so the gain will go down as 20 minus 20 dB per decade, and then we got a pole, then that will be minus 40, and then we got 0 again, so minus 20. So that's all for today. What we learned today was active loads and CMFB, and its frequency response, and these two are fully differential amplifier, which is like this, and V out is here, V out and V in. And then it requires common mode feedback. And also we learned about active current mirror load, and then its gain, and then we calculate the gain a little more accurate way. And then we also learned about common mode gain, and then also CMRR, and we calculate the frequency response. So this one, it's this amplifier. So so input is differential still. Input is differential, but the output is single-ended. So that's it looks like this. Yes. For this fully differential, they look like this. Oh, and then this is also used a lot, and it doesn't have CMFB because they have their own bias. But this amplifier usually they used in feedback mode. For example, one very good example would be a unit gain buffer. And in the frequency response, what we learned is they're different between fully differential and this single-ended. So it's like difference between fully differential and the single-ended. So here one pole, and here is two pole.